I think we covered relays okay. By the way, one little last thing on the relays. Some relays may actually come with a base, and there's different configurations on the bases. This particular one is a plug-in. As you can see, it's made so that it's only going to plug in one way. These are actually, some of these may actually have a different type of base that can be mounted, or some actually mount down as this one is, okay? So don't get confused on that either. All right. What about a time delay relay?
What page you on the school?
I'm actually following my lab for my outline. Okay. The time delay relays. Okay. I have a solid state time delay relay here, and I also have one of the old mechanical type time delay relays. You probably won't be seeing a whole lot of these out there. You know, electronics is taking over the world, right? Okay. Good or bad. All right. This is a electronic time delay relay. It has several different applications that it can be used for. This one is adjustable as far as the time is concerned. We call this the old AB switch, and it helped prevent short cycling of the compressor or the air conditioning unit. Okay, why would we have to worry about short cycling? Why would that be a problem?
It burns out the unit. I mean, it keeps starting, and stop it.
Okay, anytime you start a motor, you're going to put an extra amount of heat in it to get it started. Okay. Smaller motors generally will be able to take that as long as the load's not too great, the starting torque's not too high that the motor would stall or never start. A lot of systems are built so that they should be in an equalized state before the motor starts back up. Okay. Let's take, for example, if I have a fixed orifice system, after about 3 to 4 minutes, that system's going to stabilize on its pressures. It's going to equalize. So the motor looks at zero pressure difference to start up. But if it was using something like a TXV, then it may actually have to start up with about 100 pounds of pressure across the compressor itself. So it's already under a load when it first starts up. The time delay relays, number one, can give it time to equalize. Number two, it can reduce the amount of times that it starts up within a period to keep it from overheating. On larger motors, you may not want to start those things but about once every 20 minutes. Now, I'm talking big stuff. And the reason being is because of the added heat within the windings. So they may be timed out for as much as 20 minutes or more. Another thing that comes into mind.
So that gives it the heat time to dissipate?
Right. Gives it time to get out of there so that we're not going to have hot spots in the windings. Okay? Another problem is, and y'all know this never happens, but we never have the electricity just to blink, do we? You know, all right. You know that if you've ever been working with a computer and you don't have some kind of backup, right? You know, you've been working all day and all of a sudden, bing, bing, and you lost everything you was doing. Well, that's probably one of the most worst case scenarios to an air conditioning system, is to have the electricity to go off and come right back on. Because if the motor stops, and it will, it's automatically trying to start back up under a hard load. If there's not some type of device to prevent that short cycling, as we call it, such as a time delay relay, then it's a good chance that it's going to do damage, sit there and just actually burn itself up internally. Okay? All right. Let's move on to oh, by the way, don't limit your thoughts to time delay delays. That makes sense?
Okay.
Yeah. Right. Don't limit to being short cycle devices only. You can do a lot of things with them. I hope that as you do this lab, you'll see some of the possibilities, and it can be the same component, just wired differently. Okay, that's gonna be part of your lab. All right. Let's move into overloads. Well, we just talked about the motor possibly overheating. There's two types of overloads that we could have. One of them is more based on the temperature of the windings, internal thermostats, possibly. But there are components for the motors. This is an inline type of overload. The current, actually the full motor current goes through this device. This has a bimetal disc inside of it. As the current comes through, it would heat up that bimetal disc and cause it to warp, open up the contacts and breaking the circuit. Usually these are mounted on the shell of the motor, compressor if you will, so that it picks up the heat of the compressor too, but also is activated or opened by the current going through that bimetal strip. Okay? These automatically reset in most cases. So just because it has tripped off, be aware. If you're working with it, it can become live without notice. Okay? Let's talk about where you would not want an automatic reset on a motor. I think this is important. Can you think of a case where you wouldn't want a motor to reset on its own? Okay, I know this may sound like it's a little bit out of the line what we do, but I think it's worth mentioning. Let's say that you got a table saw, and you're operating that table saw and you run a board through there, and for some reason or another it overloads the motor and that blade stops. Okay, you're trying to unjam it. Maybe you just didn't think and didn't cut the switch off. If it resets on its own, you're in trouble. Okay? You want a manual reset in cases like that. Okay? All right, that's safety right there, buddy. I guarantee you that's safety. These are pallet duty overloads. This is a pallet duty overload. What's the difference in a pallet duty overload and an inline overload? It has to do where the current of the device that it's protecting, whether or not it breaks it directly or remotely. Okay, pallet duty, it senses the current going through, but it breaks the voltage or the current going to a contactor. Okay, I'll show you how that's shown schematically. All right. If I have a inline, more than likely, and there's several ways to draw things, you may say that's the old smiley face. Okay? This represents the bimetal disc that would do this number if the current or the heat is exceeded. Okay? The motor is directly in line with it. All right. There's a limitation there. The limitation is these contacts have to be rated for the current of the motor. You can imagine how big that would have to be if it were on some of the larger motors. Great for small stuff, but when you come into the larger circuits, and I just drew that wrong, that's a fuse. These look kind of like a question mark, and sometimes this is also used for inline. Got a question? An overload, would it be normally closed, normally open?
No.
Closed. Because we don't want it to stop the operation unless something goes wrong, right?
Yeah.
Okay? The control circuit would be going through these contacts. This would not open. Okay? This is just sensing the amount of current that's going through it. You can either have current or thermal pretty much the same thing, or you can have magnetic overloads. The operation is the same. They do have their own characteristics and on their independent or dependent applications. I think that's a little deep for us right now, but you'll learn that. Okay, that's what we was talking about, how you expand out on these things. All right. All right. You do understand that this would be going to the motor. Okay. This would be going to a set of contacts on a relay or a contactor. That would be, we'll say this is C1, this is C. Okay, that's how that would work. This would be your control voltage circuit here. This would be your load circuit. That make sense? Okay. All right. While I got it here, you can see the bimetal disc there. Okay. These two terminals would be the load going through the bimetal disc. When that disc opens, it doesn't stop this current from coming through. It stops this control circuit right here would be going to that coil, contactor coil, and it would stop this circuit, which opens in turn opens the contactor, which stops the current. Okay. This one is a magnetic. Here's the control terminals here, the load terminals here. You can see those load terminals will allow much bigger wire, so you can see how that would be quite a big disc if you had to have the whole load going through it. Not practical. Okay, that's some starting devices. Looking at it upside down here. Here's another overload device. It's the current would come through here into here. The control circuit's operated up here. Okay. Y'all see something? They don't always look the same, but they're doing the same job. Okay.
They would look the same on a schematic though, wouldn't it?
Yeah. Well, keep in mind symbols don't always look exactly the same. Though. But yeah, schematic-wise, it would be pretty much the same. All right. Capacitors. That's a real common component in single-phase units. We have start and run capacitors. Now we're going to have another lessons on capacitors as we go through, but we're going to just touch base here. This is a start capacitor. This is a run capacitor. Do y'all see anything that's physically different about it? Okay. This is a plastic type case. This is a metal case. Inside there is paste inside of this particular capacitor, start capacitor. Microfarads in relation to the run capacitor are going to be higher than the start capacitor. This stays in the circuit for a very short time. Within seconds it needs to come out of the circuit. Okay, electrically disconnected. The reason being is the heat that's produced in here. A lot of heat in a short time. The run capacitor has got electrolyte in it that's more liquid. Okay, they used to be oil filled. They're not oil filled anymore. There's actually it's a glycerin based